Let's get started. So the next talk in the session is Mark Scavenge, Waiting for Trash to Take Itself Out. I love the title. And the talk will be given by Jonas Norlinder.
Thank you. Good pronunciation. So, yes, my name is Jonas again, and today I will present a new GC algorithm called Mark and Scavenge, which is a combination of existing GC algorithms enabled by concurrent GC. And we have also implemented this in ZUC, in OpenJDK, to evaluate its performance impact. But let's start off by how memory reclamation works in a modern GC. So we have a programs heap with a bunch of objects, and these blue guys, those that we are denoting as live, and then there is some garbage objects. And the essence of the weak generational hypothesis means that most objects will be garbage at almost any given moment in a young region. So in the perspective of a garbage collector, operating on live objects is often far better than operating on garbage objects. And another goal that we have as the GC is to facilitate fast allocation. And to do that, we want to create consecutive chunks of free memory. And consider now here that we have region A, B, and C. Region A and C has 4 live objects, while region B has only 2 live objects. So region B would be something that we would call as a sparsely populated region. So an efficient GC would select region B for evacuation and evacuate object F and object E. And after updating the pointers, we have now effectively freed up the entire region B for reusage. When I say a live object, what do I really mean with that? Well, in general, a liveness property is that something good will eventually happen. And more specifically, in the world of GC, we mean that an object is said to be live if it would ever be accessed in the future by a mutator. And a mutator, by the way, for those who are not in the know of GC parlance, it's what we call an application thread because they mutate the heap or the object graph. But we don't have an oracle that can tell us if it would ever be accessed again. So we'll have to do with something else. And we use almost always, as far as I know, pointer reachability to approximate liveness. But using reachability is an over-approximation of liveness. And for moving GC, this means that this leads to wasted work. Wasted in the sense that we will move objects around in memory that are effectively garbage. So to make a more precise definition here, live really means reachable and garbage really means unreachable. And then we would have to add another notation. So we can also have objects that are dead but reachable. So in reality, what we can have is that we have reachable but dead objects, but we would still have to relocate them. And that is what we see here that we have measured. So here we have ZUC, and we have instrumented how many % of the moved object were never accessed after moving them. And each bar is a benchmark, and we see that in ZUC there is a substantial amount of wasted work going on. So what's in the design that are causing this substantial amount of wasted work? Well, ZUC for both, and by the way, old, uses Mark Evacuate. And Mark Evacuate has, in essence, 3 phases. There is this discovery phase where we mark through the object graph to find all reachable objects. And then there is a selection phase where we select the sparsely populated regions. And then an evacuation phase where we evacuate whatever we selected. All right? And the issue is that there is a delay between discovery and evacuation. And at some point between this delay, an object may die. And now also recall that this is within the context of ZGC, so this is not happening during a stop the world. Everything is concurrent with mutators. The other popular approach that one should have in mind is scavenging, that many collectors use for their young collections. And Scavenge does not have this delay as it relocates object upon discovery. So we have measured GCs that use scavenging to understand its effects. First of all, here, this plot here is the same plot I showed you guys in the previous slides with the most precise method that you can have to measure this. And here is measuring the same thing, but with the less precise method we had to use for G1 and serial because of technical reasons. And what we see is that the difference between the precise method and the less precise method is that it's not that huge of a difference. So what's the key takeaway? Well, there is a substantial amount of wasted work even for scavenging. So mark, evacuate, and scavenging is roughly on par with regards to wasted work. And another thing is one can have in mind is that on a high level, ZGC, or mark evacuate, operates on more stale liveness information, but on partially on the heap. Whereas scavenging has the most fresh liveness information you can get with pointer reachability, but it has to evacuate the entire heap. So how can we design a new algorithm that uses the best of both, which would be using as fresh liveness information as possible, but only partially evacuating the heap? We're gonna use, the first trick we're gonna use to achieve as fresh liveness information as possible is to rediscover objects and to refine the set of objects we evacuate. We will use a delay for the evacuation. So let's revisit the designs of mark evacuate and scavenge to see how we can combine them. Consider that mark evacuate, its evacuation phase, it frees sparse regions, but scavenge frees all regions. So in a hand-wavy sense, it would be safe to remove evacuate if we are still doing that. We are not going to lose any work doing that. So let's remove the evacuation phase. And mark, in mark evacuate, what it does is just traversing the heap to record reachability. And scavenge also traverses the entire heap, but to move objects. So it would also be safe to merge these passes into one. And then you will get something like this, which is the mark and scavenge in a high level. So let's start off by looking at the second cycle of mark scavenge. During the discovery phase, we are still walking the object graph to find all reachable objects, but we also move objects that are in the so-called P1 set. And the P1 set, what pages should be in that, was determined in the previous cycle in C1. And this is, of course, repeated for all the cycles, so the same applies for previous cycle, but then it's the P0 set, etc. So, in a sense, the mark scavenge cycle, it stretches over 2 GC cycles. And another thing is that the P1 set that we determine in C1, this set is further refined, not only by we are selecting by sparsely populated regions, but we are giving objects time to become unreachable. So when we come here, if we're really lucky, which we are most of the time, we don't have to do anything. And in a sense, we are also rediscovering whatever we discovered in previous phase. So what is really going on in this cycle is that we are doing mark and then scavenging for whatever is conditionally set in P1. But one does not simply just delay or ignore the most important part of a moving GC, which is to evacuate to free up memory. Your trash can is gonna get overfull. So to understand the impact of delaying, we can look at the memory pressure in mark evacuate. And the memory pressure, it starts to increase, and then we start a GC cycle, and then it continues to increase until we reach the evacuation phase where we have a sudden drop. Now, we are proposing to just get rid of the evacuation phase. Who needs that? And that means the memory pressure will increase. So, can lead to or memory exhaustion. So, how are we solving that in mark scavenge? So let's look again at this curve. Note that the memory can now decrease during mark, and we still have this situation. I'm going to show now how we solve that situation so we don't get an And because we have a set, the P set, we have a pool of pages that we know are sparsely populated, and we can evacuate objects from them to free up memory. So can you just pick one when we're getting close to running out of memory? Just pick one of these pages. Right before that, we evacuate some objects, and everything is fine. And the problem is solved. And so we call this technique just-in-time evacuation because we are evacuating just really before we actually needed it. And we can repeat the process as many times as needed in between cycles. And the worst case scenario of doing this is that we would have to do as many JIT evacuations as the entire evacuation phase in mark evacuate. So that means that the amount of wasted work will be exactly the same as mark evacuate. But that's rarely the case that we can observe that. So here in the blue bars, we have measured how much of wasted work do we have when running all of these different benchmarks. And the blue bars, they are mark evacuate in ZUC, and the green bars are mark scavenge in ZUC, and the green bars are very tiny. So most of the times we do a really great job of reducing the amount of wasted work. So what about performance then? Well, the 2020 hindsight is that, especially in concurrent GCs, you typically need to have an ample amount of headroom in order to make sure you don't put the GC on the critical path for performance. So this headroom, that hides most of the cost of having this wasted work. So benefits typically materialize when the machine is under heavy load. Therefore, the CAPO benchmark suite, those benchmarks are mostly unaffected, as most of them does not stress the machine. But we have one benchmark that can stress the machine, which is Spec JBB 2015, which is it simulates a global web store, etc. But the most important thing is that it managed to stress the machine, and we really care about the results from that. And we have a latency metric, and this latency metric is not easy to improve for a very mature GC like ZUC. And we managed to improve it by 2 to 4%, depending on what type of load you had and your heap size. And for throughput, we managed to increase it with about 2 to 8%, and we managed to reduce wasted work with about 50%. So to conclude, which is, I think, is this the key takeaway. So listen up. Reachability as a proxy for liveness leads to a lot of wasted work. And both scavenging and mark evacuate suffers from this. And we have proposed a new design that tries to solve this issue by giving objects time to die. And our GC turns this extra headroom that concurrent GCs typically have and are regarded as a cost into an asset, a buffer to delay evacuation. And while high memory pressure can be an issue, we have solved that by JIT evacuation to avoid memory exhaustion, but that increases wasted work. And we believe that Mark and Scavenge combines the best of both. And please see the paper, it has awesome pseudocode, but we have also published a full patch for OpenJDK on Zenodo and on GitHub. And thank you very much. I'm happy to take any questions. Okay.
Thank you. Really cool work. It's one of these ideas that after you watch it, you're like, why didn't I think of that? It makes perfect sense. Every time we touch garbage collection, the question that always comes up is, what about tail latency? So did you look at any benchmarks that allow you to measure tail latency? Because I would bet it would be better, but what did you measure?
So spec JBB, I think the latency score is it reflects tail latency. Let's put it that way. It's quite complex how they measure it, but that's how it is. And then we have measured actual latency percentiles for all of the Da Capo benchmark that supports it, and they were mostly unaffected. But under a heavy load, we managed to observe a 20% improvement for Cassandra's tail latencies.
Cool.
So I guess with just-in-time evacuation, like your program might spend more of its time with like a larger working set. So I'm wondering if you observed like like cache locality effects like hurting performance in any benchmarks at all.
The working set is the same or less. Depends what you compare to. What do you mean by?
I mean, like you're gonna like let your program like use more memory for longer. Like you're only gonna like lazily evacuate instead of like evacuating a whole bunch of stuff all at once.
So what can affect cache performance is like the order of how you evacuate your objects, and if a mutator moves objects, it will move them sometimes according to the access order, but sometimes just like the linear order of the region it's currently evacuating from. So depends. Super depends on the context. I really can't give a general answer.
I guess I'm trying to figure out how this interacts with peak memory use and how you would control that. And I'm thinking in particular of the heuristic from Pavel Panjeka and his student Marissa on picking the point where you fire a collection based on the square root of memory use as opposed to linear memory use. Is there any interaction here? Does it just work out the same, or do they play nicely or badly in any way?
So the point of determining when to run JIT evacuation is very, very, very hard to implement. I would say, I don't know, 50% of the project time has gone to heuristics for determining when to do stuff. I mean, oh gosh, it's so the heuristics part of a concurrent GC, it's like crazy. I think it's really understudied. I think that has been like the most hardest part I've ever worked with.
Okay, thanks.
Well, okay, I'll be quick. Yeah, great talk. I guess one thing that I didn't see discussed was contention with the mutator threads. I guess naively, because you're splitting up scavenging, compaction, I would expect that there would be more synchronization and so more contention. Was that something that you observed?
Contention where, you mean?
Between the GC thread and the mutator threads.
No, it's not something I have measured. If it would have been if it would have impacted performance, I would have noticed it probably. But yeah, thanks.